Chemical bonding. When we look at why elements and atoms join together and form compounds, or why atoms of a metal stick together and we have metal bars or steel beams, we're looking at bonding, chemical bonding. And the two types that we're going to look at today are metallic bonding and ionic bonding. Metallic bonding, you have a situation where you have these individual cations, and if this is an example, for instance, of a silver bracelet, we've got these individual core atoms, and the valence electrons, those outside electrons, are free to move in here and just flow freely throughout this metal. We often call this a sea of electrons, and that sea of electrons gives metals a lot of their characteristics. For one thing, if we look at why they're good conductors of electricity, remember electricity is the flow of electrons through something, and when you have a metal, those electrons are free to move throughout that metal and conduct electricity. So the sea of electrons is free to move. So why are they ductile and malleable? Well, you can snap a metal. You can get those silver ions close enough to each other that they repel, and they will just snap a piece of metal, a piece of wire, or whatever. But if you do it slowly and you give those electrons time to move around and cushion those cations and keep them from coming in contact with each other, you can stretch metal, you can hammer metal into thin sheets, and it won't snap apart. So that sea of electrons, again, allows, or keeps, I should say, the silver ions from coming in contact with each other, and allows that to be, again, very malleable and ductile. So what about ionic bonding? Ionic bonding occurs when electrons are transferred between atoms that have really different electronegativity values, between something that really wants to gain electrons and something that wants to lose electrons. Take sodium and chlorine, for example. Look at the sodium atom. The sodium atom has one electron in its outside energy level. Therefore, if you remember our previous discussion, sodium would dearly like to lose an electron. Look over here, however, at chlorine. Chlorine has originally 7 valence electrons, and to reach that stable octet, that S2P6 configuration, chlorine would really like to gain an electron. So it's like a marriage made in heaven. Along comes a sodium ion, or a sodium atom, and it gets close to a chlorine atom. The chlorine atom's like, I really like that electron. It would be really nice if you give it to me. And sodium's like, I didn't want it anyway. Sure, go ahead and take it. So that's what happens. I'm not sure that conversation really happens, but sodium gives an electron completely away to chlorine. And if we look at where chlorine is and where sodium is, you can see that metal and non-metal, that metal that wants to lose electrons and that non-metal that wants to gain electrons, that's a characteristic of an ionic bond. So it's a metal-non-metal kind of bond. So when the electron is transferred completely, you get opposite charges. Look at the sodium now. It's lost an electron, so it's positive. Chlorine has gained an electron, so it's negative. And we now have this beautiful electromagnetic attraction, and we have a bond, an ionic bond between those two atoms. Now when you get millions and trillions of atoms that are hooked up like this in an ionic compound, you get a lattice structure. There aren't any molecules. Ionic compounds do not have molecules. What they have are alternating chlorine and sodium atoms. So we have these nice little sodium atoms here that are positive and these chlorine atoms that are negative, and you get a lattice structure. Now, because of that lattice structure, ionic compounds have some characteristics. Most are Crystalline solids with very high melting points. That electromagnetic magnetic force of attraction is very strong, so it takes a lot of heat to melt an ionic compound. They tend to be soluble in polar solvents like water and insoluble in nonpolar solvents. Polar solvents, we'll learn a little more about those later, but they have kind of these charged ends, and they are trapped to an ionic compound like no other. If you melt an ionic compound, it tends to conduct electricity very easily. It conducts, the charges are very free to move, but if they're solid, the charges can't move. And if the charges can't move, then you can't conduct anything. So if you dissolve it in water or you melt any kind of ionic compound, you tend to get very good conductors of electricity. But they have to be melted, they have to be dissolved in water so they can move. Moving is critical. They tend to be brittle and shatter when hammered. Think about it, if you hammer these and if I were to hammer this block of sodium chloride and I were to get those charges misaligned just a little bit, instead of being opposite, like sodium chloride, positive, negative, all of a sudden I have positive, positive line up, negative, negative. Remember, those repel, and I'm going to have that crystal just shatter. So that's why ionic compounds tend to be very brittle. A piece of rock salt, if you hammer it, will shatter. Now, on your worksheet for today, what I want you to be able to do is to show how these electrons are transferred. So the first thing I'm going to ask you to do on the worksheet is to show the Lewis dot structure for each of the elements involved. If you look at lithium and fluorine, I'm not going to flip back and forth to the periodic table because you can have your periodic table right in front of you. Lithium has one valence electron, so it's going to look like this. Fluorine has 7 valence electrons, so it's going to look like this. So that's the first thing I want you to do. And then I want you to draw an arrow from the element that's losing electrons to the element that's gaining them. I then want you to write what the formula of that compound would be, and then I want you to name it. This would be lithium fluoride. Now, sometimes it's not a one-to-one matchup. Look at barium and chlorine. Barium has 2 valence electrons. Fluorine has 7. And you have to get them to match up. They have to get rid of the electrons that they want to get rid of. They have to get electrons if they want to get them. Look at barium. Barium is going to give one of its electrons to chlorine, but look at barium. Barium's still got another electron to give away. What's it going to do? It's going to need another chlorine. The first chlorine didn't have enough free spots. So here's this other electron being given off to chlorine. So what does that mean for the formula? Well, for every barium, it takes 2 chlorines to satisfy it. So the formula is going to be BaCl2. And we get the compound barium chloride. So the next one, sodium and phosphorus. Sodium has a Lewis dot structure that looks like this. Phosphorus has a Lewis dot structure that looks like this. Oops, one too many valence electrons on phosphorus. So there's phosphorus. Sodium wants to lose an electron. Phosphorus wants to gain 3. There goes 1 sodium. What are you going to have to do next? That's right, you're going to need another sodium. Is 1 more sodium enough? No, it's not. You need another sodium. And when you have that other sodium, it's going to come in here and bond right here and give another electron away to phosphorus. So what does that tell us about our formula? Exactly. Na3 takes 3 sodiums to satisfy 1 phosphorus, and we get sodium phosphide. The last one that we want to do, look here at beryllium, which looks like this, and sulfur, which looks like this. Beryllium wants to give away 2, sulfur wants to gain 2. So it looks like for our example here that that's a pretty perfect match. So that is going to be a 1-to-1 reaction, and we get beryllium with sulfur in a compound. 1 beryllium matches up with 1 sulfur, and we get the compound beryllium sulfide. Don't forget to change the ending. It's been a while since we've done these. Don't forget to change the ending of those negative ions.